So in this video, we're going to talk about how to do a hypothesis test. Now, I want to remind you of all the mechanics that are needed for a hypothesis test. And so we're using the example that says an organization has reported that teenagers spend 4.5 hours per week on average on the phone. The organization actually thinks that they spend more time than that, and they've gathered 15 randomly chosen teenagers and asked them how long they spend on the phone. The sample mean for that data, for that sample set, was 4.75 hours and a standard deviation of 2 hours. We're going to assume these times are normal. We have to remember, we have to assume that they're normal here because we've only looked at 15 people. My sample size is only 15. So I have to assume this to actually get my normal curve. And we're going to conduct a test at the 5% significance level. So in order to conduct this test, we're going to have to create a hypothesis. And that hypothesis starts by identifying the mean. In this case, we're talking about, what are we talking about? Well, this on average part talks about the amount of time the teenagers spend on the phone. So this is mu. And here they tell us that they believe that our mu is something bigger than what's being stated. So we know that the part that we believe is the alternative. So that means that mu is less than the 4.5 that is being stated. And that the claim is that mu is equal to 4 or greater than or equal to 4.5. And remember, there's always some kind of equality in this first part. And this is what we're trying to test of what we believe. So when we write this, and I wrote this wrong, they think that it's greater than 4.5. So I'm going to go back here. That's greater than 4.5, which means that this has to be the opposite, less than or equal to 4.5. And so because when I look at this now, I can tell that this gives me the direction of the test. And the test is a right-tailed test, which means that I'm testing things to the right of the actual mean value. So to get the critical value, we need a couple things. Critical value is based on the alpha level, the significance level, alpha, and that's equal to 0.05. And then we also need the sample size, which was n equals 15, because that's going to give me the degrees of freedom for this test, which are one less than that, which is 14. And so I'm trying to find the T star at 14 degrees of freedom. And that's going to create the rejection region, which is out here. And remember, because it's a right-tailed test, we're putting all of this rejection region at alpha in that region, and anything that falls inside of here is going to be what we fail to reject. And so when we set our rejection region, in order to find this t value, we use the inverse normal function, or the inverse, in this case, inverse CDF of the t distribution. And the t distribution wants the degrees of freedom, and then it wants the area that we want out there. We want 0.05 all on the right tail. Now, here's what's going to happen. Because it's in the right tail, the value I'm going to get in my calculator is going to give me left tail area. I can use 0.05 or I can use the other side of the curve, which is 0.95. But either way, I'm going to get the same number. One's going to be positive, one's going to be negative. We need to make sure we look at the positive version because we're on the right side. So we have inverse CDF, T dis, 14 degrees of freedom, comma, 0.05. Notice it's negative, but I want the positive. So this is equal to 1.761. So what this does is that tells me that any value that is 1.761 or greater is going to put in the reject region. Any values that's less than that, it's going to be plausible or we'll fail to reject it. To get the test statistic, which we call T, T is equal to my X bar minus the mean, the stated mean, the hypothesized mean, divided by the standard deviation over the square root of n. I come back to the problem. They tell me that my sample mean, X bar, is equal to 4.75, and my sample standard deviation, S of x, is equal to 2.0. So I can plug those in now. Here's what I get. This means that t is equal to 4.75 minus mu divided by S of x over the square root of 15. That's my n. And again, this mu, we already know this value mu, the hypothesized mean is 4.5. So when I calculate that, here's what I get. Divided by 2 over square root of 15. This is equal to 0.0433 or 0.433. So here's what happens. I've created this rejection region out here, which is at t star 14 is equal to 1.761. Here's the mean at 0. Here's the value that I've gotten for my actual t value. So my t-score is 0.433. Now, there's two ways to test this. This right here, I can use this value right here and compare this value right here and compare it to this region right here. And I'm already seeing that I'm falling in the fail to reject region. But I'm going to go further. I'm going to use the actual p-value now. To find the p-value, the p-value is the probability of getting a value as extreme. So the p-value is the probability of getting a test statistic, which in this case is 0.433, which is as extreme, which means it's equal to as extreme or even more extreme. So even more extreme would be anything going this direction, if in fact the null hypothesis is true. So to do this, we're going to use the t-distribution at 14 degrees again. And this time we're going to set our minimum value. You look here, you can see your minimum value is your minimum value starts here at 0.433 and it goes all the way out here to infinity. So this we're going to do, find that p-value, t-dis at 14, find cumulative. We have our minimum value is 0.433, our max value stays at infinity. This probability here is equal to 0.335. So now there's a couple ways we can do this. We can come up with our decision. Either way we go, we see the first way is based off of the critical value approach. The critical value approach says your t-score, t is, in this case, less than t star at 14 degrees. Because of that, we're going to fail to reject, and we fail to reject the null. And remember, when you look at this, you can see here's your t-score, here's your actual t critical value at 14 degrees. And you look to the left, right here, when you go to the left, we're falling in, our value is falling somewhere over here. Close to 0, by the way. It's close to 0. And we're falling in the fail to reject region. If you do the p-value approach, the A p-value approach this time says that your p-value of, which is 0.433, is greater than your alpha value. So 0.433 is greater than I'm sorry, this is 0.335. Is greater than your alpha value of 0.05. And again, anytime the p-value is greater, that means the likelihood of it occurring is also pretty good to occur. So again, here we would also fail to reject HO. Now that we have failed to reject HO, the last thing we're going to do is we're going to make our conclusion. So our decision is we have failed to reject. Remember, in this particular test, what you're saying is that a person is considered innocent. Remember? The only way we can take away the innocence is if there's enough evidence. Because we have failed to reject their innocence, they are still innocent. Why are they still innocent? There is not enough evidence to support their guilt. And our guilt in this case is HA. If you want to take it back to the entire original problem now, what this is saying is that there is not enough evidence to support that the mean is greater than 4.5 based on this.